I couldn't get hired by Atari because they were going through a problematic time in 1986. Imagine if people could see the world the way we see it. In April of 2003, the US invaded Iraq, and that logo was on the screen for up to 10 minutes an hour as they were explaining what was going on in this new war. And we nearly took down Google because it turns out that we were using more than half of the bandwidth of the entire company. And that's why Google Maps is better than Apple Maps. Some new situations where governments are ruining GPS.
Welcome back to NeuroBridge. Have you ever opened up Google Maps? There's a good chance that you have. You probably most likely take tools like that and Google Earth for granted, but there was a time when they didn't exist. Today's guest is the visionary that scaled and built those tools, Brian McClendon. He's the inventor and co-founder of Keyhole, the startup that became the foundation Google Earth. His career spans decades of groundbreaking work from building GPUs before they were even called GPUs to leading the entire business unit at Google, overseeing Geo, so Google Maps, Street View, Google Earth, and he led that for over a decade. And he was inducted into the National Academy of Engineering and was recognized by the United States as a literal champion of the Earth. And today, he is the Chief Technology Officer at Niantic Spatial, where he is pioneering the large geospatial model to build 3D maps for the future of augmented reality and robotics. In this episode, Brian is going to tell us about the history of geospatial systems, from his workstations at Silicon Graphics to the logistical nightmare of mapping the world through Street View and purchasing that data from vendors, to almost crashing Google servers and giving us incredible inside information about demand that scaled such incredible product. Without further ado, here's my podcast with Brian McClendon. Thank you so much, Brian, for willing to join us on NeuroBridge today. Super excited to hear more about your perspective and your experience building such incredible products.
Thank you. I'm glad to be here.
Absolutely. So let's start off with an interesting question. And this is like a trivia fun fact. Your childhood home is the default center point of Google Earth. I would love to know more about how your childhood and upbringing influenced the way in which you thought about mapping the world. And what are some experiences that led you to building geospatial systems at scale?
Well, it's a long and winding road, but I started with computer games, video games in the early 80s. So the Pac-Man, Asteroids, Missile Command were the very first, stand-up arcade games that came out right when I was a teenager and spent a lot of time in arcades. And I was inspired by pixels and graphics and eventually wanted to do computer graphics. I got an Atari 400, wrote some games with that. Ended up taking computer science, electrical engineering at University of Kansas. And ended up, one of my projects was a computer graphics related one, but my main project at the University of Kansas was actually building a computer CPU. And this inspired me to want to go, work in video games or work in computer graphics. And I couldn't get hired by Atari because they were going through a problematic time in 1986, but I did get hired by a company called Intergraph. And after that, Silicon Graphics. So I spent 10 years building sort of the very high-end computer graphics of the day, which you might know as GPUs, back before they were called GPUs.
Awesome. I think, the fact that you built GPUs before they were called GPUs just kind of shows the extent to which you've had experience in the tech field from a long time.
Mm-hmm. Yep.
So I wonder, how did you think about this transition from playing video games to actually building the graphics? Like, what was, when you first completed the CPU, like, how did it make you feel to think about the fact that you've built the system that you once played on?
I think it was the very early days of computing, and so there were not really that many people involved in it. There was no internet yet. Although there was this thing called Usenet that was just getting started at the time. And so it was hard to find a lot of people doing the same thing unless you went into the industry. And so for 2 years I was at Intergraph, but then for 8 years I went to Silicon Valley. And there, seeing the machines that were possible and then seeing the applications that were built on top of it. So many of the video games were actually designed on SGI machines. So the modeling software of 3D Studio Max and Maya ran on SGI originally. And this was how many of the early video games that had any kind of 3D were created, because the PCs just couldn't do it at the time. But we also built these smaller and smaller chips, and one of the projects that was being done right next to me at SGI was the Nintendo 64. So the MIPS R4000 plus a graphics chip that was built by SGI, that was the Nintendo 64. And so Super Mario 64 was sort of the ultimate or penultimate 3D graphics game that coming into the home. And that was built the hardware built by people sitting right next to me. And then, of course, many of us played that game religiously when it first came out in sort of the mid-90s. After that, just watching all of the other computer graphics applications get built on SGI machines. So we saw, computational fluid dynamics, we saw, scientific visualization, and then we saw movie editing. Discrete Logic's Flame application was how almost all movies were edited. And of course, Studio Max, 3D Studio Max and Maya were used for movie animation as well. And so things like The Abyss, Terminator 2, Jurassic Park were all built on our hardware, and in some cases in our labs because they needed the newest hardware to work on it.
Exactly right. I mean, started a revolution because like that kind of compute, as you kind of said, like most people weren't actually into that field at that time, and after it, the explosion of compute that was available and the way that, as you said, so many different industries were able to leverage it is just really incredible. But I mean, that's only the first of multiple revolutions, frankly, that you have been a part of or started. So I actually want to ask you about the mapping revolution and the Google Earth revolution. So obviously, you built Keyhole with John Hanke, you scaled it to Google Earth at Google, and you later became the first CTO at Niantic. So what lessons from building a map in a project of that scale carried over to your work at Niantic, and like what lessons did you pick up?
Well, I'll go back and sort of catch the history up right at the end of Silicon Graphics. So one of the things that was very hard to use in the early 90s was satellite imagery. We had satellites out there. You could look at slow or non-moving images and pictures, but interacting with it was very hard. And so one of the last things we did at SGI was build some hardware that allowed for what was called an infinite resolution texture. In fact, it ran on the graphics card Infinite Reality, and it was used to enable a texturing algorithm to treat the entire planet effectively as a single texture map. And this allowed, demos of this sort of worldwide texture. Now, of course, even then we didn't have, satellite imagery for the whole world at the same resolution. So we had to deal with low-res imagery, a single pixel per square kilometer in some cases, all the way down to a few insets of high-resolution satellite imagery. And we had this demo in 1996 called From Space to Face. And that inspired us to say, imagine if people could see the world the way we see it. And zoom in and out and go anywhere, not just in this one special place that we had done the demo for. And so in 1998, PC graphics were getting better. They still probably weren't quite good enough, but they were getting better. And there was a lot more satellite imagery, and we started this company, Keyhole, with a demo on a PC that was similar to what we'd done on workstations just 2 years earlier. The NVIDIA 3DFX and ATI were all building graphics chips for PCs. They were not really quite good enough yet, but they were almost good enough that you could hope that soon they would be. So we started this company, got it funded, hired John Hanke in 2000, got it funded in 2001, and then struggled with the fact that the satellite imagery, it was expensive, and that 3D graphics cards weren't good enough yet, or certainly popular enough yet. You couldn't assume that somebody had one in their machine. And finally, you needed fast internet, where 128 kbits was not fast enough, and that was ISDN, which was pretty much the best that people had. So, until cable modems came out and sort of ubiquitous high bandwidth T1s and ADSL from the phone company came out, we struggled. And so for a couple of years, Keyhole, basically sold to enterprise customers, real estate agents, travel agents, but consumers just couldn't run it. And that all changed as graphics cards got better and ADSL and cable modems became more common. And we suddenly had this moment in 2003 and 4 where people were able to download and actually use it. And we showed it on CNN. We got a deal with them where they would use it for showing where news stories were, as long as they put our logo on the bottom right of the screen. And it turns out in April of 2003, the US invaded Iraq, and that logo was on the screen for up to 10 minutes an hour as they were explaining what was going on in this new war. It was a rough time, but it was very good to be able to show where things were happening. And so it exploded. And one of the things we immediately learned is that if everybody starts using it, network bandwidth gets crushed and servers get crushed. We had to go, replicate our servers multiple times in our tiny little data center in a basement in Palo Alto. Then that taught us we needed more, and that's when Google came in.
Yeah, I mean, as much as this is a vision oriented solution that you guys have produced at Keyhole Google Earth, it is more so an infrastructure related question, because at the very beginning you were struggling with realizing the fact that most people didn't have graphics cards, or graphics cards weren't good enough, countless different issues when you guys were starting to operate at scale, the fact that the network compute needed to be enough to support multiple users, to support consumer. I think that is the critical point that really deeply impresses me about Google Earth, is the fact that you are literally mapping the world. The amount of compute required for that, the infrastructure needed, is just, quite frankly, very massive. So I would love to know, how did you pick up insights from building an infrastructure project of that scale and carry it over to Niantic?
Mm-hmm. Well, so the infrastructure we had at Keyhole was a startup's company's worth of infrastructure. Mm-hmm. And so we were approached by Google, who wanted to buy us, and selling out, isn't always the right answer, but in this case, they had several things that we needed. One, they had money, and they wanted to A, buy the company, but B, they wanted to buy a lot of satellite imagery to give us more coverage of the Earth. Two, they had network bandwidth, because they had already installed these data centers, at least in the east-west of the United States, and they had just started on Europe. I don't think they had Japan yet. And so they had bandwidth. And they also had storage. So they had these big rack servers running this thing called GFS, and that was the Google file system. And it was really built as a sort of background processing storage, but we, Keyhole, came into Google and immediately started serving live data from GFS. We were the first ones to do that. And we had to, because our data size was so large. Our database was, at the time, probably a few terabytes in size, which sounds not like a lot these days, but back then it was quite a bit. And we wanted to grow that much larger. So obviously Google had all this. So we came in. The other thing we did was, Keyhole had been a $70 and then a $30 product, per person. Google decided we were going to make it free. So Google Earth was launched in June 2005, and it was free. And in the first few days, hundreds of thousands and then millions of people downloaded it. And we nearly took down Google, because it turns out that we were using more than half of the bandwidth of the entire company. And it turns out search pays for the bills, and Google Earth did not. So they moved us to a separate set of virtual IPs called they renamed it the Risky VIPs. It was the Keyhole VIPs, but they renamed it the Risky VIPs because they put products that they didn't care as much about over there so that they wouldn't interfere with search or ads. And this became very important later. And we built out a huge database. We started with the satellite imagery that was promised, but we eventually went to aerial imagery. So we flew a lot of airplanes and collected high altitude and low altitude aerial imagery, which was much better. And then eventually Street View. So Street View was started in 2007, 2008, and eventually covered 20 million miles of roads around the world, and ended up with a 20 petabyte plus database by the time I left. And a lot of this was Street View data. The satellite and aerial was actually dwarfed by the amount of imagery being collected on the ground.
Wow, half of Google's compute got taken up. That is something. I wonder, how did you guys go about Street View? Because I know there are a lot of chronicles about it, but it seems to me like an even harder problem than just relying on satellite imagery.
I mean, in some ways, yes, in some ways, no. From the technology of the data collection, getting an accurate aerial camera and certainly flying a satellite is quite hard. Putting a camera on a car these days is trivial, but back then, the first attempt that Google did was a very custom-built van with some big discs and several cameras on the rooftop, and you might imagine like a Waymo car, 20 years earlier. And the problem there was it was pretty expensive. So the next version of the Street View camera was much cheaper, kind of tacked on to an existing car, almost any existing car, and was up on this mast that got it above the car so that it could see more of the road around it. But then it was simply just triggering pictures every few meters, and also surviving the heat and rain and thermal and ice and all the other things that a Street View car ran into, and collecting it and programming where to drive, figuring out where the cars could drive to cover as much of the world as possible. So there was a lot of logistical issues around getting that many cars out on the road. There are hundreds of Street View cars driving simultaneously. And then there was the much harder problem of getting those cameras moved into all the different countries you had to drive in. We started in the US, Mexico, Canada, but eventually I think they've covered over 50 countries now, 60 countries. And just the legal issues around getting hardware on into that country and then tacked on to the local car, and then driving and not getting into trouble, turned out to be, a full-time job for hundreds of people.
I mean, I can imagine, because if anything happens to that technology, it's challenging to replace it, introduces latency in getting that data. So you have to make sure that not only is the car safe, it's also accurately recording the Street View footage. It's definitely a challenge. I wonder, how did you guys use AI and ML at Maps in kind of all of your projects in mapping at Google?
Well, my favorite example goes to our desire to make our own map data. Because one of the first things that happened after we launched Street View is that people would look at the Street View pictures and they loved them and they thought they were really cool. But they would look at the picture and then look at our map data with an address or a street name or a one-way and say, your picture shows what's really true, which is that it's a one-way street and your map is wrong. And so it turned out that the map data that we had been renting from TomTom and Navtech, Teleatlas and Navtech, wasn't very good. It was the best in the world, but it was not great because it's very hard to get a map data up to date because the world's changing around it. And Street View, we had just sort of covered the whole United States very, very quickly. And we realized that we needed our own map data. And instead of doing what they had done, which was driving around in a van and taking notes and taking pictures when appropriate, we just used our Street View data and did it all sitting at the workstation. So you collected the data, and then operators would visit questionable locations. They would use government data as the base map, but then they would fix things based on the imagery. And for satellite imagery, they'd align the roads to the satellite, and they would correct one-ways and street addresses and things like this. And they did a lot of that manually. But one of the hardest problems with street data, and this was not, Teleatlas Navtech didn't even have this, was accurate geocodes. So your house is at this exact address, this house is at that exact address. Usually what they had was from 200 to 300 Main Street, and we'll guess 235 is right there. It was a guess. But knowing exactly where each house was is pretty hard. With Street View, if you had geographically aligned your Street View data and gotten it precisely oriented, you could know where every single address was if you could detect the address in the Street View picture. And so we ran an algorithm to scrape all 1 to 5 digit numbers from all of the images. And this was just a sort of a generic process. Then we sent it to the OCR software of the day, optical character recognition before AI. And the best that you could do is about 35% recognition. And so we said, this isn't good enough. We started using humans, and we sent it to operators that we'd been, drawing roads with, and they would type numbers in. So they got really good at this. They could do 10, 20, 30, they could probably do 2 or 3 per second, like they were fast.
Okay.
But even so, very expensive, doesn't scale. So the next thing we did was we sent out those same addresses to the users of this thing called reCAPTCHA, which would be everybody else on the planet. And we'd send a picture of one of these 5-digit numbers or 1 to 5-digit numbers and one of those squirrely twisted letter things where we knew the answer. So if you answered both of them and got the letters right, we assumed you got the numbers right as well. We'd also send that same number to somebody else. And so we used humans doing reCAPTCHA to get all of our numbers. And we did that 2 billion times. And that actually mapped a large part of the world, but it also didn't fully scale. And so, and this is almost apocryphal but true, that in summer of 2012, I believe, a summer intern came around saying, we're working on this thing called Google Brain, and we need big data sets. Do you have anything we can work with? And so Google Brain became known as TensorFlow later, and was built by Jeff Dean. We handed them 2 billion pictures and 2 billion labeled numbers for those pictures. And this summer intern comes back at the end of the summer with an algorithm that's better than any 2 people are on any picture of a number. And so from then on, we used this ML applied to Street View, where we automatically extracted it, we triangulated the location, and we recognized the number. And that's why Google Maps is better than Apple Maps.
Wow, I mean, I think I didn't really draw that connection until now, and hearing it from you is just like, that is crazy that you wow. I mean, I think that the fact that you guys did 2 billion of these samples is just like a huge scale function. So, and obviously it had significant applications to Google Brain and beyond. I mean, obviously there were mapping applications, but even beyond that. So that's just really incredible to see how tech is a forcing function. Sometimes you'll do something and then you'll never realize how that data is used in another way. So that's really cool for me to kind of hear about that. I've heard a lot of the stories of, how these really foundational products were built. I'm curious, looking forward, where do you predict the future of geospatial AI going? Like foundation model autonomy, gaming, something else entirely? Like, what's one lesson you wish you'd learned about working on foundational tech?
Well, I think just going to the last story, data sets matter. So 2 billion labeled images, extremely valuable, can solve multiple problems. Data is the new oil. And, that's an old punchline from probably 10 years ago, right at the beginning of ML. But it's still true, right? These models, whatever they are going to need large data sets to train them. And, what we've found is that obviously with language, with LLMs, we've already scraped the entire world. Like there's almost nothing else you can put into an LLM these days. And now they're figuring out other areas. But there are lots of other data sets. And for robotics, for, these ego position, out the eyeballs kind of views, training what people do, that's some interesting data. The real world is an extremely interesting data set. And if you have large collections of imagery and video from the real world, whether it's geographic or spatial, can you train models that can predict what the real world looks like? And I think that we've seen this already with some, what they call, general world models, World Labs or Cosmos are these both doing prediction, one trying to synthesize sort of near fantasy or near world 3D reconstructions in the case of World Labs, or Cosmos, which is actually synthesizing video and encodes not just the 3D nature but the 4D nature So it has some concept of physics and objects in motion such that there's self-consistent result. That's great for video, but that doesn't actually generate the real world. And I think that, what we are focused on in Niantic is taking some very large data sets that other folks don't have and building a model of the world that predicts the real world and combines that with these other sensors, whether they're satellite data or street level imagery or handheld collected imagery, and could predict what the world looks like today from data that you've had in the recent past or from similar locations. And I think we have a lot of new data sources coming, but at the moment the focus of most folks is not on geospatial as much as it is on just sort of geotypical. And Niantic is focused on the geospecific.
Wow. I think the fact that if you are able to source data from the world, you can train a model that predicts new states in the world. I think that's a really big step towards AGI. And I feel like a lot of the times people hyper focus on linguistic applications of AI, specifically LLMs in today's ecosystem. But I truly believe that world models, geospecific modeling, as you mentioned, creating these huge amounts of data in order to train these future world models are just as, if not more, critical. So this is a problem that obviously you've been heavily experienced in, and I really I'm very happy about the fact that someone as experienced as you is building something like this, because it's going to be invaluable going forward in AI in general.
I agree. I think it's a hard problem, and we haven't solved all of it yet, but we certainly are seeing a lot of applications. And one of our biggest areas of understanding the real world is, can you localize a person? And this is something that Niantic's been working on. It's with respect to augmented reality. If you're wearing glasses or you have a headset and you want to know exactly where you are, turns out that GPS doesn't work reliably, and the compass in your phone and in general is just terrible. Magnetic orientation is not very good. So a visual positioning system built from one of these models, allowing a wearer of glasses or somebody with a phone or something where the GPS doesn't work to find themselves relatively precisely, not just where they are, but where they're looking, then allows the rest of the system to understand the world around it. Because these VLMs, are pretty good at saying, yes, that's the Eiffel Tower, you must be standing, about here. But if you're at 82nd and 5th Avenue, it looks a lot like many other places, and the VLMs are actually really terrible at it because there's nothing special as far as it knows, because they don't understand geographic information. So we're building a visual model that does understand pretty much everything in the entire world.
When that launches, I think that will be really fantastic, because you can, at any location that's been mapped, you can quite literally triangulate your exact position. That would also, I think, even potentially solve a lot of these problems with relative mapping and potentially in-room mapping. Like if you're standing in a room, you usually, because GPS has a margin of error of I think something like 100 meters, correct me if I'm wrong, you don't know where you are as opposed to someone else.
The GPS quality varies depending on how many satellites it sees. Outdoors on a perfect day, it's 1 to 5 meters. 1 meter is extremely unlikely. 5 meters is pretty likely. But indoors, it's just terrible. You might get a signal from GPS. Half the time, you're just getting Wi-Fi signals, and Google and Apple are figuring it out because they've reverse mapped Wi-Fi to GPS over time, and they're guessing where you are. And then cell towers are much worse than that. So at the moment, the location tech is pretty, not very good. And this is, especially true when GPS satellites are either not visible or in some new situations where governments are ruining GPS. The Russians are very good at actually knocking down all of GPS, or worse, making you think you're somewhere else. And so they've spent a lot of money on attacking GPS, and you need to be robust to those kinds of things.
Fascinating. All right, I notice we're coming up on time on our chat, but I do want to ask you one last question. What is one career or life lesson you want to share with the next generation of builders and innovators?
So I was thinking about this, and I'll give a specific example of a more general truth, which is that as you go through life, you can either sort of trust what the computer tells you, or you can question it and check it against your own intuition. And if your intuition is broad and well understood, then you can actually save yourself a huge amount of time when the computer makes a mistake. The narrow example of this is that if you have good mathematical estimation skills and numeric skills, like if you know what 12 times 12 is, if you know the difference between 100, 1,000, a million, just intuitively, and that you can deal with powers of 10 up to the trillions, if you know this well enough, you will immediately see many people make mistakes in many, many dimensions. People overestimate something by a factor of 100, and they just don't know because they don't have the intuition for it. Having the specific mathematical intuition and checking, usually people give you the numbers and the result, and they screwed up the multiplication somehow. All you got to do is do it in your head, estimate it, and if it's off by, then question the answer. So get good at math. Just basics. Don't spend the time on it. It's worth it. Computers and calculators are fine, but you can't depend on them because many people make typos that are undetectable if you don't have the intuition to detect them. The broader problem here is get a good education. Understand, these large language models are very confident in telling you that this is true. And it's going to sound true, but if you have a good background education, many of those things will just be flashing red lights of stupidity that you will immediately question and dismiss that as an LLM hallucination. But without it, the tendency will be to trust these models, and that's a mistake. You need an intuition about life so that you can get past the cases where these computers are just wrong.
Absolutely. I think building the intuition is more important now than ever because a lot of the times, hallucinations, like confidence in LLMs is actually a bad thing. We want the model to be less confident than it actually is. So I think if you have that intuition, you're going to definitely do a lot better than people who have zero clue and just blindly kind of accept what's being put in front of them.
Exactly.
All right. Well, thank you so much for spending the time today with me on NeuroBridge, and we really appreciate you coming on and sharing your expert insights on geospatial, geospecific mapping, and really appreciate it.
Absolutely. Happy to be here and great to talk to you, Tarush.
Absolutely.